I'd like to thank you all for coming today, everyone who's here both in the room and watching online. I'm Scott McLaughlin. I'm a faculty member here in the Department of Mathematics and Statistics at Memorial. And I'd like to thank all of you, and I'd also like to thank the Atlantic Association for Research in the Mathematical Sciences, who is funding Professor Patrick Farrell's visit here this week and who is funding this lecture. So thank you very much to AARMS for the support. I'm very pleased to get to introduce Dr. Patrick Farrell. He completed his undergraduate degree at the University of Galway, his PhD at Imperial College in London in 2010. He stayed there as a postdoc for a few years before he won an EPSRC 5-year research fellowship that moved him to Oxford in 2013. Since that time, he's sort of risen through the ranks. He was appointed as an associate professor in 2016 and promoted to a full professorship in 2022. Dr. Farrell has many, many distinguishing things on his record. He was a winner of the Wilkinson and Fox Prizes in 2015. He's won the London Mathematical Society Whitehead Prize and the Charles Broyden Prize, really for his fundamental contributions in computational science and engineering, in fluid mechanics, for optimization problems, and for the solution of nonlinear equations, which is what he's here to tell us about today. So please take it away, Patrick.
Great, thank you very much. It's like being at the Oscars. I've got so many people to thank, right? So I've got Scott to thank for this fantastic introduction. I've got you to thank, especially the people in person, but also the ones online, for coming on this beautiful sunny day in St. John's when you could be hiking up Signal Hill. And I'd also like to thank the Atlantic Association for Research in the Mathematical Sciences for making this visit possible. And indeed to the team at the back from Memorial for doing such a fantastic job. So when I thought I should give a public lecture, you know, I wrestled for some time about what exactly should it be. And I thought that I wanted to tell a story that spanned many centuries, a story that's core to our society, to our civilization, to the way that we interact with the world, a story that describes how far we've come, and also a story that ends with some kind of glimpse about how far we have yet to go, about how much we don't understand. And so with these requirements in mind, I decided to discuss Newton's method. So really, this talk is about a dream. It's about a dream, and it's about how we pursue this dream. And the dream, it's not a common name, but I'm going to call it the Cartesian dream, after René Descartes, who was one of the first people, maybe the first, to sort of cash in geometric problems for algebraic ones. So, you know, if you were an ancient Greek mathematician and you're hanging out in Alexandria and you want to find where 3 circles intersect, you're going to do it geometrically, right? You're going to construct those circles with protractors and compasses and these kinds of things. But René Descartes said, no, the way that you should do this is that you should write down an equation that describes the points on one circle, an equation that describes the points on another, and an equation that describes the points on the third, and then see where they intersect. Where can you solve all these equations simultaneously? And generalizing from this idea, the dream is that when we want to know something about the world around us, we're going to write down equations that relate what we know and what we don't know, and then we're going to solve those equations for what we don't know. And why do we want to do this? Well, because we need to understand the universe quantitatively in order to build things, in order to design systems, in order to predict what's going to happen if we do an experiment before we do it. Right? You know, it's fine to put some rocket fuel in a rocket and, you know, light the fuse and then let it go, but how much do you need in order to escape the Earth's gravitational pull? How long is it going to take until that rocket gets to where you want it to be? You need numbers. You need to quantify things. And that's the heart of the Cartesian dream. So let's start with some simple examples. So I appreciate that many faculty members in the room are intimately familiar with this idea, but this is a general audience, so I wanted to make this concrete with some concrete examples. So let's look at something that most of us do most days, especially in Newfoundland, where I'm a bit lost, is where on earth am I? Right? So how do we solve this problem? We solve this problem with GPS satellites and their friends, right? And so how does GPS work? The story, of course, is a little bit more complicated, but at its heart, the way that it works is that each GPS sends you a signal and it tells you, this GPS satellite is here, so you know its position, and you know how far away it is, right? You have to correct for how long it takes the signal to travel through the Earth's atmosphere and so on, but that's the basic gist. And so in order to determine our position, which we don't know, we'd like to know, then we solve equations, like the distance from my position to the first satellite is some known value, and the same for the other satellite, and the same for the other satellite. And I'm going to solve these equations for my position. And so if we did the opposite of what Descartes did, if we sort of tried to see this geometrically, the way that we might approach this is, well, for each satellite, you draw the sphere, that's the radius of the known distance from that satellite that you are, and then wherever you are going to be is going to be the point of intersection among these 4 satellites, among these 4 spheres. Okay, and mathematically, at least this very simplified model of GPS becomes something like this, that the distance between my coordinates, x, y, and z, that I don't know, and the coordinates of the satellites x1 through x4, y1 through y4, and z1 through z4 are some known values. Okay, so that's one example, and this is really how the GPS unit on your phone works. Another example, orbital mechanics. So in 1609, Kepler wrote down this equation. He didn't know where it came from. It was a phenomenological observation from decades and decades of astronomical observations that had been painstakingly compiled, but he figured it out. And so this is a fundamental equation in orbital mechanics. And so this is, previously we were solving for 3 unknowns. Here we just have 1 unknown, which is x. Okay? And so the way that this works is very roughly, you use a telescope to look at some astronomical body or comet or something like that, and you measure its period and something called its eccentricity, how elliptical its orbit is. And then from that, it's very straightforward. There's a few formulae. I could have written them down, but you can just look them up on the Wikipedia to calculate what m is as a function of time. So given the period and the eccentricity, you figure out m. And then from this equation, you want to solve for x, right? So m and e are known, and you need to figure out x. But there's no way that you can isolate x equals some known function of m and e from this equation. It's not so easy. Okay? So we have to solve this equation in order to figure out x, which is called the eccentric anomaly. And then once you know x, there's a simple formula to figure out what the position of the planet or the asteroid or whatever it is you're looking at the given time. And it's not just sort of 1 real number or 3 real numbers or 10 real numbers or 100 real numbers. This idea goes very far, right? And it underpins almost everything around us. From understanding the weather and climate, we solve differential equations to simulate what the weather is going to do tomorrow and what the climate is going to be like in 10 years' time, 100 years' time, whatever. And it's really crucial to be able to solve these equations because while I have enormous respect, infinite respect perhaps, for my experimental colleagues, there's just a lot of things you can't do. You can't make a copy of the Earth and double the carbon dioxide concentrations and run it for 100 years and then see what happens, right? So we have to solve equations in order to do this. Just such experiments are just totally infeasible. I liked this picture especially because we can see where we are, right? And see where the Gulf Stream wending its way past us. Or I saw this beautiful talk just a few weeks ago by a good friend of mine at NASA who's trying to design how do you land 50 tons on Mars if you want to put humans there. You think how much stuff do humans need? You will go camping, right? You live in Newfoundland. How much stuff do you have to pack in the back of your car? Well, if you're going to go to Mars, then you need about 50 tons of stuff in the back of your spaceship. How do you land 50 tons? Well, you can't use a parachute, so instead, you've got to deploy thrusters that sort of fire as you land in order to slow you down. And how on earth are you going to design such a thing except by solving equations? You cannot reproduce Martian gravity. You cannot reproduce a Martian atmosphere, right? It's just not going to happen. So you need to solve equations in order to make it possible. Or another very beautiful example of this sort of reaching for things that are beyond experiments is one of the great scientific success stories of recent years, which is the detection of gravitational waves by LIGO. And the way that this worked is that we needed some super dramatic event in order to detect this gravitational wave signal because gravitational waves are so weak. And that was going to be, people thought, the merger of 2 black holes. But if you want to know what gravitational wave signal you should be looking for, you cannot rig it so that you take 2 black holes somewhere far away and you merge them together and then you send the signal over to the detector so that you know what you're looking for, right? You just can't do it. You have to solve equations in order to identify the pattern that you're going to look for in the noise. And that's exactly how the detection happened. The detection fundamentally relied on solving equations. Okay, so that's the dream. That's what we want to do. But how do we do it? Right? How do we solve these equations? So let's consider the friendliest kind, right? Sort of the kinds of equations that obsessed algebraicists for millennia, and indeed still do. Many of our colleagues, perhaps some people in the audience are experts in these. polynomial equations. Okay, so for some kinds of equations, you can just write down the solution, right? And maybe, one of the stories of mathematics, one of the themes of mathematics over the millennia is broadening our concept of what it means to solve a problem. Okay? So for this kind of problem, what does it mean to solve it? It means that you just write down what the solution is. So if I tell you what a and b is, you want to find x such that ax plus b equals 0, well, this has solution, x equals minus a over b, right? We all know that. Actually, many people didn't. So for example, the ancient Babylonians didn't know that. They didn't know that you could move the b to the other side of the equation. That came later. They used to solve this equation with numerical methods, amusingly, right? I thought that was very funny when I learned that. And, at least if you go to school in Ireland, like I did, you'll have met this equation many, many times, a quadratic equation, where now instead of a first power of x, we've got a quadratic power, right? And we want to find the roots of this. And I don't know about you guys, but I was tortured with this problem. I must have applied the quadratic formula 1,000 times, right? I was bored of it after the third, but somehow that was what the syllabus required, right? Invented by an Indian mathematician in the 600s. And then about 1,000 years later, Italian mathematicians figured out the formulae. They're long and complicated, so nobody really uses them, of how do you find the solutions of cubic equations and quartic equations. And there it stood for another 300 or so years until someone realized that for most problems, you can't just write down the solution, right? You can't just write down x equals some formula, some explicit formula. And the theorem, it's kind of disputed. It was, that I'm going to ascribe it to Abel, but historians can reasonably fight over this point. But it's not so important who invented it or who discovered it. What's important is the result, that there are polynomial equations of degree 5 and higher that you cannot write down simple formulae for their solutions. And this blew people's minds, right? Because this made the concept of what it meant to solve a problem wrong or incomplete, irrelevant, right? There are these important problems, quintic equations, and we cannot solve them in the way that we've been solving problems for 2,000 years. So how do you pursue the Cartesian dream, right? I mean, these are a really nice class of problems. Lots of problems aren't polynomials. Kepler's equation isn't a polynomial. If we can't even solve polynomials with an explicit formula, what do? Most problems are harder than this. So really there are two solutions, two responses. So one, I would say, is to prove things about the solutions. So maybe you spend your time trying to prove that solutions exist, right? So the fundamental theorem of algebra says that, well, that problem has 5 solutions in the complex plane, and that's good enough for me. I don't need to know what they are. I just need to know that they're there. Or maybe you try to extract qualitative information. Maybe, in this particular context, you could try to find out how many positive or negative or imaginary or sort of complex solutions there are, or, some kind of information about their magnitudes, or perhaps some information about, as you send some parameter to this limit, you get some kind of picture of what they might look like, but it's not telling you just the answer, right? It's just getting some information about it. The other response, and the one that I'll be exploring, is to devise algorithms for computing these solutions, is to generalize our concept of what it means to solve a problem. Rather than an explicit formula, I'm going to make an algorithm. I'm going to make a computational procedure that can iterate until some condition is satisfied. And that computational procedure, there's a typo, it will construct a sequence that converges to the solutions, right? That's the other response, is give up on the hope of an explicit formula, but rather make a computational procedure. And some of my colleagues, I talk a lot with the historians of maths that I know, and some people say that, well, this is maybe the root of the division between pure and applied mathematics, with the top one being the pure response and the bottom one being the applied. Okay, so how might this go? Well, first let's just reformulate the problem a little bit. So given the mean anomaly and the eccentricity of our orbit, let's use Kepler's equation, we want to compute the x that satisfies this equation here. And to develop algorithms for this in a generic way, we'll just move everything to one side of the equation to do the move that the Babylonians didn't know. So we'll just move everything over to the left-hand side of the equation, and I'll call this formula as a function of x, f of x. And so we're looking for special input values. Some input x, I'll call it x star, that makes a particular function, this f, which I'll call the residual, achieve the output of 0? What inputs can I plug into this function that give me 0? Okay, and I can always solve equations in this way, by moving things from one side of an equation to another. Okay, and so these special inputs, the x stars that satisfy this relation that make your output 0, I'm going to call them roots. So solving equations is the same as finding roots. Okay, so Kepler would have a picture like this in his mind, right? You've got, let's say, a comet or something orbiting the sun, right? And this is a fairly elliptical orbit with eccentricity 0.6. And if we plot this function, this m minus x plus e times sine of x for some value of m, here's what it looks like. Okay, so you give me 2, it gives you this answer. If you give me 4, it gives me that answer. If you give me 6, it gives me that answer. And we're looking for the input that makes the function 0. And so this crosses this line at exactly one point here with this green dot. And at least by eye, by graphing, we can guess that this is something like 2.1. But this isn't, we can't always graph our functions and look at them, right? We want to be able to solve these algorithmically. We want computational procedures that will approximate this result to arbitrary accuracy, as many digits as we need. Okay, and so to that end, we're going to meet two algorithms. So the first is a beautiful, simple idea called bisection. And bisection is one of the things that surprises me that our ancient mathematical ancestors didn't know. If you're ever caught in a time machine and you're sent back to the ancient Babylonians or the ancient Greeks and you want to become as famous as Euclid, then the only thing that you need to remember from this lecture is bisection. Because although they could have and should have known it, we have no evidence that they knew it. There's no records, there's no theorems, there's no results, there's no clay tablets. So here's how bisection goes. So it's based on a theorem, as all good algorithms are. And the theorem is the following. So if we have a continuous function, like the one for Kepler's equation, and we know two input values, a and b, with the following property, when I plug those input values into the function, I get opposite signs. One of them is positive and one of them is negative. Okay? If that happens, then there must exist an x star, a root. Of course, roots don't have to be unique, but there exists at least one between a and b that satisfies f of x star equals 0. Okay, so that was proven by Bolzano in 1817. And so this immediately inspires an algorithm, right? So what we're going to do is, if you tell me a and b, I'm going to bisect. I'm going to check the midpoint of the interval between those two values. And I'll call that c. And then there's a trichotomy. I have three possibilities, right? So the first is that f of c equals 0. So we're done. We found a root. So we can all go home. The second is that f of c has the same sign as f of a. Let's say they're both positive. So that means that I can replace a with c. Now, by Bolzano's logic, there's a root somewhere between c and b. Or f of c has the same sign as f of b, so that means that I can replace b. So I can replace b with c. So now I've shrunk the interval in two. Okay, and so let's see how that goes. So this is, again, Kepler's function for the same comet with eccentricity 0.6. Okay, and let's suppose that, by a bit of doodling, we find two input values that one has a positive residual, one has a negative residual, and so we're good to go. So I construct c, which is the midpoint, and then I evaluate the function there. And I don't actually need to know what the value of the function is. I only need to know its sign. So in this case, f of c is positive, so I can replace a with c. So in the next round of my algorithm, I replace a with c, and so now I'm at this situation. And then I take the midpoint, and then I evaluate the function, look at its sign. In this case, it's negative, so I can throw away the b, and carry on. And so in this way, every time we engage in one round of this algorithm, we either solve the problem or we shrink the bracket by half. So I hope it's clear to everyone that this does indeed converge. Let's do an example where maybe I tabulate the results so that you can kind of see more precisely how well it's going. So let's look at a different function. Let's try to find the fixed point of cos. Okay, so I want to find the x such that x equals cos x. Okay, and a bit of doodling. Let's check minus 10 and 10. Minus 10 gives you a strongly negative number, f of 10 gives you a positive number, so we're good to go. And so we can proceed. And so as we go through the iterations of the algorithm, our best guess for the root C is converging, but it's converging really slowly, right? So the true solution is 0.739085, but we're getting there, but it's going to take a long time, right? And evaluating x minus cos x is not so difficult, but what if evaluating f is very expensive, right? Or we need to do this trillions of times. We need to do better. And the first reference that I could find in the history books to bisection was from Cauchy's famous book on analysis, the course on analysis, in 1821 that he wrote for his lectures at the École Polytechnique that famously no one in his audience could understand because he was a terrible lecturer who used to mumble and assume that you all knew it already. But, full of good ideas. So we'll forgive Professor Cauchy. So when it applies, it's guaranteed to converge. It's very simple. It's very robust. You understand it after a minute. Its convergence is slow. That's not so good. It can be hard to find the initial data to set up the problem, hard or even impossible. Really, the killer problem is that it doesn't generalize to higher dimensions, right? So this works fine for solving Kepler's equation, but it's not going to help you if you have a GPS problem to solve, and it's certainly not going to help you if you want to predict the weather or simulate the merger of two black holes. So let's take a look at an example where it'll never work. So if we take a very simple problem that we can all solve in our heads, if your residual is x squared, it's always non-negative. So that means you can never find two inputs, one positive, one negative. So there are some roots that just you have no hope of finding with bisection. So you're sunk. When it applies, fine, but this really isn't the tool for the job. So that's why we should move on to a better idea, a different idea, Newton's method. And Newton's method is really the core technology that we use to solve equations, and a core technology that underpins technological, scientific, industrial civilization. So here's the idea. So now we've got a different residual again. We want to find its root, which is this black dot here. Okay, and I don't need two inputs, I just need one. I'll call it x0 here. And what I'm going to do is I'm going to locally approximate the function with a linear model. So I'm going to build a linear model of the function. My function is nonlinear, but locally at least I can build a linear approximation and hope that that's going to do something useful. And the best linear approximation to my function is this tangent line, which is why I call it T0. Okay, so I build this tangent line, graphically that's what I'm doing, and then I say, well, okay, I don't know how to find the root of the nonlinear problem, of the nonlinear residual, but I do know how to find the root of its linear approximation, right? Because I can solve linear equations. We know how to do that. So my next guess for the root will be exactly here, where this tangent line crosses the x-axis. So I go there, and then I do the same again. I build the tangent line once more, and now that takes me much closer to the root, and then that point becomes x2, and so on. Okay, so I'm going to solve equations by successive linearization. I'm going to build linear models, solve those linear models, and keep going. Now, how do you build a linear model of a function? It's all well and good to draw a graph and then sort of get out your ruler and draw a tangent line. But how do you do it? Well, the answer is calculus. And I appreciate that some members of the audience don't know this, but don't know calculus. But it's fairly straightforward, so don't be too scared. So given a function, its derivative, all you need to know is that its derivative is a function that tells you the slope of that tangent line, right? That's what a derivative is. Okay, so if I calculate the slope of the tangent line to the curve at a particular point, that's just its derivative. But I also know that the tangent line joins 2 points, right? So it joins xi, f of xi, and it joins xi plus 1 and 0. That's what defines xi plus 1, that the tangent line is 0 there. So that means that I can write the slope of that tangent in 2 different equal ways. One with the derivative and one with the formula for the slope of a line. And then if I just rearrange this equation for xi plus 1, this is the map. Okay, so you give me xi, and then I compute xi plus 1 by evaluating this. So I take the function, divide by its derivative, and then subtract all that off from the current guess. Okay, so this is a general way of trying to iterate to a root, right? This is a much more general idea. But of course, it has roots in antiquity. So the first instance that I could find of what we now call Newton's method was for calculating square roots, right? So if you're a carpenter and you've got one edge of length 1 and another edge of length 1, and you want to know how long should you cut this piece of wood to join them up, it's not just enough to say that it's the square root of 2, whatever that may be. You need to you need to know how long that is. So how do you calculate what the square root of 2 is? Well, what you do is you look for roots of x squared minus c, for whatever c is the number you want to calculate the square root of. And this was known to the ancient Greeks in Alexandria. This is called Heron's method. And so if you apply Newton's idea to the specific example, then this is what you get. And if you simplify this algebra a little bit, it turns into what Heron realized. So just simplifying this expression gives you this. And this is very intuitive, actually. This is another idea that if you got in a time machine and got there before 8060, then you could use this to become rich and famous. So here's the idea. If I have an approximation of the square root that's less than the square root, right? Then c over that number is going to be bigger than the square root, or vice versa. So if I average them, then I'll get something that's closer to the square root. That's the idea, right? That's how Heron figured it out. It took another 1400 years or so to figure out how to compute pth roots, how to compute cube roots and quartic roots and so on. And that, as far as I can tell, was figured out by Jamshid al-Kashi in Samarkand under the Great Khan in 1427. Not normally known as a hub of mathematics, but there you go. This was it. Okay, so let's take a look at how this works. So previously, we looked for the solution of x equals cos x. And we tried this with bisection, and it was slow. We ran out of patience. Okay, and here's some digits of the true constant, the true fixed point of cos. Okay, so let's apply Newton's method. All right, and let's just use an initial guess of 0. It doesn't really matter what we use. So then we figure out that x1, the next iterate, is 1. And so my error is about this. And then I'll underline any digits that are correct. x2 is this, and the error is about 10 to the minus 2. x3 has twice as many correct digits or so, and it's 10 to the minus 5. x4 has roughly twice as many correct digits, and it's 10 to the minus 10. And x5 has all correct digits as far as I could compute in double precision. Right? And if you wanted to compute 100 digits or 1,000 digits, you could keep going, and it would be doubling every time, so long as you had a computer to execute the arithmetic. Okay, so this was much, much faster. Bisection took about 50 iterations to get the same accuracy. Okay, so when it works, most of the time, of course, there's caveats, and the caveats and the edge cases are exactly where your lecturers in analysis love to go. Right? So I haven't seen your exam papers, but when I write exam papers about Newton's method, that's where I'm always going. But most of the time, sometimes we can focus on the details and lose the big picture. The big picture is that Newton's method converges very, very fast. However, there's a catch. Newton's method trades speed for reliability. So here's a simple example. Here's a nice cubic polynomial. We have an exact solution for this, right? The Italian mathematicians give us a formula. It's not so hard. Okay, and so here's its residual. These numbers aren't crazy. The root is over here somewhere near minus 2. And let's start with an initial guess of 0. 0 is not too far from minus 2, but you would hope that this is a reasonable thing to do. So let's build a tangent line at 0. Look where it crosses the axis, and it crosses the axis at 1. So that becomes my next guess. And then I go to 1. I build a tangent line. And where does it cross the x-axis? It crosses the x-axis at 0. So I go back to 0. And then I go back to 1. And then I go back to 0. So while the solutions of the equation are attracting fixed points of this Newton map, it turns out that there are other structures, here in this case, a period of length 2, that's kind of super attracting, right? That Newton likes to lock into this and oscillate back and forth between 0 and 1 in a way that doesn't get us anywhere at all, right? So that kind of, already for this simple problem that you can see very visually what's going wrong, it suggests that there's something untrustworthy about Newton's method. And even when it converges, Newton's method can behave really oddly. It's really bizarre. So let's take a look at another cubic polynomial, and here I'll write it out in such a way that you can see what the solutions are. So the solutions are x equals 4, or x equals 1, or x equals minus 3, and I'll use some initial guess, okay? And then if I run my code, it's written in MATLAB, you can find it online. Then after 24 iterations, we converge to minus 3, which is the solution, so that's fine. But we've gone some pretty weird places in between, right? All of these roots are nice small integers, but along the way, Newton picked up guesses of minus 144 and had residuals of, minus 3 million and so on. But okay, if that's what Newton wants to do, so be it. But now let's try changing the last digit of this initial guess. And now when we run the algorithm, it ends up at x equals 1, somewhere totally different. So I make the tiniest perturbation, an infinitesimal perturbation, to where I was, to the initial guess, and I get somewhere completely different. So, somehow intrinsic to Newton's speed is this chaos, is its instability with respect to the initial data that you supply. So changing the initial guess can completely change the answer. And of course, this drove a lot of studies in holomorphic dynamics and chaos theory and all these kinds of things, and we'll see some pictures of this later on. So let me make some historical remarks. So when I was choosing what to do as an undergrad, I thought between either being a mathematician or a historian. So that's why I love looking back at the past and reading the old manuscripts. So Newton invented this in 1669, but he only published it in 1711, and his method actually was nothing like the one that we know. He didn't make any connection to calculus, even though he had invented calculus, which is kind of strange. And he only applied it to polynomials, right? So this was quite odd, but Newton invented lots of other things. He was very clever, so we'll sort of let him off. John Wallis, who was one of Newton's contemporaries, who was a professor in Oxford, the Savilian Chair in Geometry, which still exists, my friend holds it in Oxford. He actually published the same method before Newton in 1685. So he invented it later, but he published it before. So, there's a very slightly different world where we would call it the Wallis method instead. And I guess being from Oxford, I should have called this talk about Wallis's method, but never mind. And Joseph Raphson in 1690 simplified it considerably. He showed that, you didn't need to do all these elaborate calculations, but they still only applied it to polynomials, still only to scalar equations. And so the big breakthrough, the next big breakthrough came with this, that in real life, most problems aren't just solving for a single real number. You're solving for multiple inputs. So let's consider functions that take in several inputs. So where n is 3 or 4 or 100 or 1,000,000 or 1,000,000,000. So we want to find x stars that are vectors of numbers such that some function maps to 0. And this was figured out by Thomas Simpson in 1740, so close to 100 years after Newton invented it. And the title of the book is so good that I had to write it down and I had to read it, that it's essays on several curious and useful subjects in speculative and mixed mathematics, illustrated by a variety of examples. And I invite the faculty members here, whenever you next write a book, and you're thinking about the title, try to lean something more towards this. I think we've gotten a lot more boring in the centuries since. I really love this. And in fact, Newton's method extends much, much further. So unlike bisection, which is sort of dead in the water after you've got more than one variable, one of the great heroes of mine and one of the great mathematicians of the 20th century, Leonid Kantorovich, figured out in 1948 that Newton's method can actually be defined for nonlinear problems in infinite dimensional spaces, and in particular, apply it to differential equations. So he figured out how you can generalize Newton's method to Banach spaces. And this is what lets us apply Newton's method to those infinite dimensional problems that I mentioned at the start, like the Navier-Stokes equations for the flow of water in the world's oceans, or the Einstein field equations that describe the merger of two black holes, and a million other things besides. More or less every high-tech object in our lives, your car, has been through the ringer of Newton's method in order to figure out what's its best shape. Why do all cars converge to the same shape? It's because aerodynamics has gotten a lot better. So when does it converge? Right? This is really the the crux, because as mathematicians, it's not just enough to know that, okay, we're able to solve this particular problem. We'd like to be able to solve problems reliably and automatically. I want to know that when I apply Newton's method to some instance of this problem, I'm going to be able to solve it. I'm going to be able to converge. Because we've seen that if you don't have just the right initial guess, then Newton's method can go totally haywire. So we want theorems, we want proofs. So let's take a look and see why this might be hard and sort of where we are at the minute. So let's look at a problem in two variables. So we're going to look for a complex number, which you can think of as a pair of real numbers. Okay, so we're looking for the roots of unity, the cube roots of unity. So this is just a polynomial, but now instead of x, I'll use a z, so because I want it to be complex. Okay, and we know what these solutions are, right? The cube roots of unity are this, 1 and 2 conjugate complex numbers. And what we'll do is we'll take some subset of the complex plane, and we're going to color each point as follows. To each point in the complex plane, we'll assign a color. And the way that we'll do it is we'll run Newton's method from that initial guess. So the point where we are coloring is our initial guess. And then we color it according to which root it converges to. Okay, so we just want to map out a picture of where Newton's method will take us from any given point. And this is what it looks like. I think it's absolutely beautiful. Of course, I've seen this many times, and maybe many of you have seen it before, but every time I see it, it's something to gaze at in glory, right? That somehow the fundamental technique that we use to solve equations, to pursue the Cartesian dream, has at its core such incredible complexity from such an incredibly simple formula, right? This is, many people who go into mathematics do it because of its aesthetic beauty, and I think this is one of the finest examples of exactly that. So maybe just let me orient you. So this problem, remember, has 3 solutions. So there's a solution over here, there's a solution over here, and there's a solution over here. Okay, and we'll call them the red solution, the green solution, and the blue solution. And so if I start with an initial guess here, Newton will just contract me very nicely to this blue solution. If I start with an initial guess over here, I'll get to this red solution. If I start with an initial guess over here, I'll get to this green solution. But all the interesting action is on the border between these sets, right? So if I'm here and I make the tiniest perturbation, and say I'm at a green point just here, and I make the tiniest perturbation, then I can get to a blue zone or a red zone. And in fact, the borders of these sets are fractals. So if you go to a live rendering, I remember first when I found this out as a kid, and I coded it up in my 486 at home, and it took, 20 minutes or 30 minutes or something to render a picture. And now you can do it live, right, in your web browser. It's amazing. So here is the same Newton fractal running on a website. And so indeed, as you zoom in on one of these structures, you see that it's blobs on blobs on blobs on blobs. And no matter how far you zoom in, you get the same structure back again. It's absolutely beautiful, right? Full of infinite complexity. And in fact, so with these tools, it's so nice that you can take some of these roots. So maybe let's take this root here that's at 1, and you can drag it around, and then you can see it live exactly what happens. And you can make all kinds of beautiful artworks, right? So if you're trying to decorate your undergraduate hall of residence or something, this is a fantastic way of doing it surely going to promote some conversation. Here's just one more example for the Newton fractal for the polynomial that we met before when Newton had this fixed cycle of length 2, and it's just beautiful, isn't it? Just this infinite sea of complexity that you could study for your whole life. And so this explains in part why we don't really have a satisfactory theory of convergence, of when Newton's method will converge. And what do I mean by satisfactory? I mean one that I can predict in advance in some kind of useful way. So maybe let me just go back to the Newton fractal. Our current results, what they do is you look at the solution, and we can draw a ball around each root, and then you can guarantee that if you start Newton's method within that ball, you will converge. Okay? So there's a ball around this root, a ball around this root, a ball around this root, and these balls are the Kantorovich balls after Leonid Kantorovich, who proved this theorem. But I hope sort of looking at this picture that I can convince you that, just being able to say something about a ball that looks like this is not really very satisfactory when there's this huge sea of the plane that will in fact converge to this. This huge sea of the plane that will in fact converge to this. A huge sea of the plane that will in fact converge to this. And all of the sort of the complexity of, let's say, the green blob here and the green blob here and the green blob here and the green blob that's attached onto that and so on. Right? So these conditions that we have, the theorems that guarantee when Newton's method will converge, they are sufficient, they're true, right? If your initial guess happens to satisfy them, then you will converge. But they're by no means necessary. They're a million miles from necessary. Most of the time when Newton's method works, we do it without a theoretical underpinning. Okay, and so many famous mathematicians, not least among them Cauchy and Kantorovich, have given insights into when Newton's method will converge, but our existing theorems don't describe what happens in practice. They don't actually really underpin the computations that our colleagues in the sciences and engineering are relying on every day. And so I would say that a major open problem in applied maths is, can we build a useful convergence theory for Newton's method, right? Something more descriptive than what we have at the moment. And maybe that's vague, maybe this is a hard problem to write down precisely. Or is there another algorithm for solving equations with this property in such a way that we can guarantee? Okay, so I should say as well that there are bounds on how much we can prove. So for example, there are undecidability results by a fields medalist, Stephen Smale, giving limits on how much we're able to say about Newton's method's convergence from arbitrary points. But there's a big gap between what we have and everything, right? And we'd still like to be able to fill that in. Okay, so let me conclude. So Newton's method, invented by Newton in 1669, extended to systems of equations in the 1740s. The first useful convergence theories by Cauchy in the 1820s, and then substantially advanced and extended to infinite dimensional problems in 1940s by Kantorovich. And then what will be the next big contribution? Because it's for sure the case that our story of our understanding of how we solve equations is by no means complete. So I hope that it might be someone in the audience. I hope it might be one of you who's able to prove in this century or the next or the century after something else, something deep and insightful about this method. Can we have an algorithm for the Cartesian dream that is both fast and reliable? And with that, I'll conclude. Thanks again to AARMS and to the team at MUN for making this possible.
Thank you very much, Patrick. Are there questions? Lee?
I'm curious about the Newton set that you had up there. The actual boundaries of the solutions, the white kind of parts of that color. Just wondering what you could say about those particular spots.
Yeah, these have been studied quite a bit, actually, and there's a lot of very interesting results. So here's one theorem that I think is far from trivial. So let me just first say what the boundary of a set is, for those maybe who haven't studied it. So the boundary of a set, is there chalk somewhere? Okay, there's no chalk, I'll wave. No, okay. Oh, well spotted, yeah, okay. That wasn't where I would have looked. Oh, to be tall. Okay. So if I've got a set and I want to know what its boundary is, the boundary is going to be the set of points with the following property. If you put a little ball around that set, around that point rather, it always includes points that are not in the set and points that are in the set. Okay, so that's what its boundary is. And now that we know what its boundary is, there's a really interesting statement that you can make, which is that the boundary of the blue points is the same as the boundary of the red points is the same as the boundary of the green points, right? And somehow this is what gives you this property that if you make an infinitesimal perturbation to the initial guess, you can get any other route, right? So once you're sort of on the edge of the region of convergence, actually for these problems, you can find all solutions just by zooming in on one tiny little ball. And that's why somehow you get this blob on blob on blob structure. Because, imagine that you started with, some blue card and some green card and some red card, and then you told your teenager, okay, I want you to make it so that whatever point on the boundary always includes colors of all of the three colors, right? So you might, draw something. Well, that's 4, but okay, good enough. That looks like this, but then you kind of have to put blobs of the other color, and the other color, and the other color. And then in order to make that work, you have to put more blobs and more blobs and more blobs. And that's somehow what drives this fractal structure.
Those boundary points are still initial condition guesses, right?
Yeah.
And, if you make that initial condition guess, it doesn't go anywhere.
Well, there will be initial guesses that don't converge to any solutions.
I do have a question. Well, first of all, that was a very inspiring talk. The premise of your talk was based on finding solutions for equations and different methods for it. But in our talk, before the presentation, you mentioned the importance of multiple solutions to a problem. Can you talk a little bit about that?
Yeah, well, this is one of my main research interests, actually, is calculating multiple solutions of nonlinear differential equations. And this is a big problem, because if you have a problem with multiple solutions and you only find one, then there's a real danger that sort of your pursuit of the Cartesian dream will make everything break horribly. So maybe let me draw what I mean. I'll go over here for variety. So imagine that we've got a solution set or a solution space, right, in which I'm looking for solutions. And let's say that I've got a problem with 2 solutions. Okay, and I want to know what is some physical device going to do, what is some physical situation, how is it going to play out without actually doing the experiment. Okay, maybe I can't afford to do the experiment, or it's something like the black holes where I've got no control over it. Okay, so if we converge to one solution, like this one, and we don't find out about the other solution, then we can be bedazzled, we can be fooled, right? We can build our designs based on our belief that this is what's going to happen. But actually, if nature chooses this guy, then all of our calculations could be correct, but we're completely wrong because our calculations were incomplete. So that's why finding multiple solutions when they exist is really important. And so I work in my own research on techniques for calculating multiple solutions of these equations. And the basic idea is this. So if you give me, an f of x equals 0, and I find one solution, x1, with this, what I'm going to do is I'm going to construct a g of x equals 0, so a new problem to solve with Newton's method or whatever else that you like, with the property that g has all of the solutions that f does, except for the one that you know, in some sense. And so then you can apply Newton's method to g, and then you hopefully find another solution, and then you can build another residual and apply Newton to it, and build another residual and apply Newton, and so on. And in this way, you can calculate tens or hundreds of solutions when they exist.
So, silly questions. So, what programming did you use to get the picture?
So these ones, I should. This was from the Wikipedia. So, but this is actually, I think it's written in WebGL. So this is actually running in a web browser. So this is running live on whatever probably crappy graphics card that this computer in the desk has. So what you can do now with graphics processors is amazing. So this I think is in WebGL. But you can write this in MATLAB, or you can write this in Python, or you can write this in anything else that you like. And now computers are so fast that you can do this live.
My questions conduct just around the cubic polynomial, or can you do it higher order polynomial?
Sure. Yep, you can compute Newton fractals for any kind of problem you like. It doesn't have to just be cubics.
In the points that were on the boundary and do not converge, can they also be in boundary, right?
Yeah, so there's different ways that you can not converge. And Newton's method, sort of, if you view it from the point of view of a dynamical systems map, has all kinds of interesting behavior that you can get 2 cycles, or you can get 3 cycles, or you can get cycles of arbitrary length. Or you can get points where Newton's method sends your iterate off to infinity in some direction.
And you have something that is goes all wrong, like it's
Yeah, that also happens. Yeah, so there's not sort of it's like, you know, the unhappy families of Russian literature. There's all different ways to be unhappy.
I think this is a stupid question, but I just need to be clear. The shading is aesthetic, right? Three colors.
The shading is aesthetic, but it carries some semantic information. It's not a stupid question at all. The shading tells you how easy it was to converge. So the shading, I should have said that actually, so thank you. The lighter it is, the fewer iterations are required to get to some tolerance. Right? So the darker points are somehow harder.
So it's only aesthetic in the sense that it's not actually aesthetically motivated.
Yeah, I guess it's both. It both carries semantic information about sort of the behavior of Newton's method, but it also looks pretty.
Are the boundaries always fractals, or are there certain examples where they're just one size one color and one size the other color?
There's a nice example where it does do this, for this sort of simple behavior. So something that looks like this. Well, you know, this is one region and that's another, and that's for quadratic polynomials. So if you draw a Newton fractal for a quadratic polynomial, you just get a plain partition. There's a line of points that don't converge, sort of the ones that are equispaced between the two roots, but other than that, you get simple pictures. But for all other degrees, you get something that looks like this, precisely because of this property that the boundary of every set has to coincide.
There's a similar algorithm in the machine learning or artificial intelligence. I'm not sure if you're familiar with backpropagation and gradient descent. I was curious how that would compare to Newton's method. It appears as though this is significantly faster than gradient descent.
First of all, they're solving two different problems, is the first thing to say. So backpropagation is a way of calculating derivatives, and gradient descent is a way of minimizing or optimizing some cost function, right, between what the neural network is doing and what you want it to do, basically. You can apply Newton's method to optimization problems, but the way that you do it is that there's something called taking the optimality conditions, which is you write down a system of equations that the optimum must satisfy, and then you try to solve those equations, right? You try to treat that as a system of equations. So probably the example that you're familiar with is if I have, if I want to minimize x in Rn, f of x, and f is sufficiently smooth, then I know that that's going to happen when grad f is equal to 0, or in one dimension when its derivative is equal to 0. And so this is now a system of equations that I can think about solving, and I can apply Newton's method to that. And remember, the Newton's method takes the derivative of the residual, so that means that if my residual is a first derivative, then Newton's method will take the second derivative. Okay? So that's why Newton's method somehow is faster, because it's in optimization. And many people do use Newton's method in optimization, but it has more requirements in the input. You have to be able to calculate and deal with second derivatives of your functional. Whereas the great thing about gradient descent is that you can try to minimize this problem only with information about the first derivative. But somehow, philosophically, you expect that if you give someone more information, more structure about the problem, they'll be able to solve the problem faster. And maybe that's why Newton's method, when you can make it work, is faster than gradient descent.
So Newton's method is like x minus f over f prime, right?
Yep.
So is it possible to start in a region where it should converge, but at some point during the iteration, you end up getting f prime to be 0?
Yes.
And then can it somehow just not converge anymore? Is that possible?
Yeah, exactly. So every iterate, you need that the derivative is not 0, and in general, in higher dimensions, that the derivative is invertible. And if you hit an iteration, or hit an iterate where that no longer holds, then Newton's method, you have to give up the ghost and stop. Your iteration terminates, or you have to do something else, right? And in fact, there's a really interesting analog of Newton's method. Sort of, you can treat Newton's method as a discrete version of some kind of continuous dynamics. So Newton's method was this. Minus f dash of xi inverse f of x. Okay, but so I could treat that as something that looks like xi plus 1 minus xi over 1 is equal to the same guy, right? And then now you can think of this as the discretization of a time derivative. So I could instead think about the ordinary differential equation, which I think is being lectured by Scott McLaughlin. You should go if you're not. Okay, so this is somehow the continuous analog of what the Newton map is doing. This is called the Davydenko differential equation. And this has some really nice properties. And in particular, you can prove the trajectories of this equation, if you can compute them, will either end in points where this isn't defined or at roots, right? So there's something, even when Newton's method isn't converging, and there's lots of points where Newton's method won't converge, there's something about the underlying continuous map that is for which, of course, the Newton direction, the step is the tangent, that somehow does have this kind of global convergence property. So there's something really right about Newton's method, even in cases when you're far away, and even in cases where it isn't converging.
Well, I think we should all thank Patrick again for a
Thanks very much.
fascinating lecture.